Hello, Professor Simmons here. We're going to review how to solve first-order linear differential equations. We'll go through the theory here, then we'll do a couple examples, and we'll wrap up by reminding ourselves why we know there is one unique solution to such a differential equation. So here's the form of a first-order linear differential equation. Remember, what makes it linear is that there's a y prime term and there is a y term, but there are no mixed terms that multiply those. There's no function of y, and so on. Here we have a factor p of x multiplying the y term, and there's a factor q of x on the right-hand side of the equation. Now, if q were equal to 0, the equation would simply be separable, and we could put it into this separated form with the y's and the x's on opposite sides, integrate both sides, and end up with a solution here. Y is a times an exponential, and the and a is, I should say, a constant, and this exponential factor is simply the integral over x of p of x, the coefficient of y in the original differential equation. So, if q is not equal to 0, we have to think a little more. But it turns out that if you think about what the function y times e to that same I factor looks like, when you take one x derivative of it, it works out to look like that same exponential multiplied by y prime plus p times y. But that reminds us of our original left-hand side of the differential equation we're interested in. So if we multiplied the differential equation we're interested in by the factor e to the I, then we have something that looks like this. E to the I multiplied by y prime plus py is equal to q multiplied by e to the I. And if we want to try integrating both sides, being optimistic, we remind ourselves that, oh yes, this left-hand side is now a total derivative. So integrating a total derivative, we know what the answer is, that's fine. And on the other hand, on the right-hand side, we see that we'll simply have to integrate q, which is a function of x, multiplied by that exponential, and add a constant, since we're doing an indefinite integral. So we find that after a little rearrangement, y is equal to e to the minus I, just rearranging from the line above, times this integral of q e to the I, plus our constant b times e to the minus I. And remember, this factor I is just the integral of p of x from the original differential equation. So starting from the original first-order linear differential equation, we have essentially an algorithm for how to solve it. So let's go on and use that general principle in a couple of examples. So the 3 steps in solving a first-order linear differential equation are first to put it in so-called standard form, meaning where the y prime term stands alone with no coefficient. That's what allows us to use the algorithm. Then we have to find that integrating factor e to the I, and then we can solve. So here's an example straight out of the textbook. X squared y prime plus 3xy equals 1. That's not in standard form. We have to divide through everything by x squared to put it in standard form. And now we see that p is 3 over x, and q is 1 over x squared. We can calculate the integrating factor I, we can calculate the integrating factor first by calculating I as the integral of p of x, which works out to the log of x cubed, and then e to the I, our integrating factor, is x cubed. Finally, we can solve the integral by just using the formula. E to the minus I, q, e to the I dx is simply, well, there's an x to the minus 3 for the integrating factor. Inside the integral, our 1 over x squared partially cancels against our x cubed to give us a very simple x dx integral, and we end up with an answer 1 over 2x for that part of the solution. And then we have to add on a constant times 1 over the integrating factor to give us the second term in the solution. So the full answer is y is 1 over 2x from this integral plus our additional constant over the integrating factor term. That's the end of this example. We'll now do another example. Let's do a second example. As you can see, this one is already in standard form, so we can immediately identify the factors p and q. To calculate the factor I, we simply integrate cosine x to obtain sine x, so our integrating factor e to the I is e to the sine x. So the integral we need to do to help solve the differential equation is e to the minus sine x times the integral of e to the sine x sine 2x, that's our q factor, dx. Now, we'd like to rewrite this sine 2x in terms of sine x and cosine x, which gives us that factor of 2. And now we'll just quickly run through a few steps for actually solving the integral. You might, for example, want to change variables from x to u to simplify things a little bit. In this form, it seems like it might be a good idea to perhaps employ integration by parts, which then shows that the integral of u du will yield, of u du e to the u will yield this result here. And placing that back in the expression above, we now have to remember that u was in fact sine x. So we find that the integral that we're trying to do is now this external factor 2 e to the minus sine x times the result of doing the integral, which is sine x e to the sine x minus e to the sine x. So a lot of the exponential factors then just cancel each other out, and we're left with 2 times sine x minus 1. That's the piece of the answer coming from the integral. We also need to remember that there will be a factor from the constant of integration as well. That's b multiplying 1 over the integrating factor, so e to the minus sine x. So putting the two pieces together, we have the entire answer. Now, having done a couple examples, we'll go on to talk about how we know that the answer we're finding is the unique answer to this linear differential equation. Now we'll take up the interesting question of how we know the answer we found is the one unique answer for an ordinary first-order linear differential equation. So let's think of this linear differential equation in its standard form, y prime plus py equals q. Let's suppose the contrary. Suppose that there are two different functions, y1 of x and y2 of x, that each solve this differential equation and that both give the same value at some boundary condition, at some value of x that we'll call x naught. These match up. Could they really be two separate, distinct solutions? Well, now if y1 is a solution, then it's true that y1 prime plus py1 equals q, and that y1 evaluated at x naught has some value that, let's call it a. And the same would be true of y2, as I write down here below. Now, let's think about what happens if we subtract y1 from y2 to form a variable y hat. And let's in fact subtract these two sets of information from one another. We see that by subtracting the differential equations from one another, we find y hat prime plus p times y hat is 0, because the two right-hand sides above are identical. And we see that y hat evaluated at x naught is 0, because y1 and y2 agreed for that value of the boundary condition. Now this is a linear equation, so we know how to solve it. And it's in fact got q, q is 0. So we know it's just separable, and the answer is exponential. Y hat is the value of y hat at x0 times e to the minus the integral of p of x dx. But y hat evaluated at x0 is 0. So y itself vanishes, except in some extreme case where p is singular, but then you'd have other problems with your differential equation. So in other words, what we found is that y1 minus y2, or y hat, vanishes for any value of x. So y1 and y2 agree at every value of x. So the ordinary differential equation really does have only one solution after all, and this drawing is not realistic. The curves y1 and y2, if they match at any one point, they match at every point. And this is what we mean by uniqueness.